Hello everyone. Recently, I came across an article on Uber's official engineering blog which talked about how Uber scaled their backend to serve 40 million plus read requests per second. That's right, per second. And so the story starts from their own internal database called Docstore. Now, Docstore is their in-house MySQL based database. They built it on top of MySQL, that is, and it stores a lot of data because Uber has a lot of transactions, it has a lot of ride requests, it has a lot of driver location updates, and a lot of different data to manage in general, which should scale up to petabytes in terms of storage. So they already had that, but their database was effective enough to manage 10 million plus requests per second still. So what they had built already was pretty good, but it could not scale to the level that they wanted to. So they wanted something even bigger. Why is that? Because of their different business verticals. So as the number of teams grew, their initiatives grew, the number of microservices also grew. Each team wanted their own services in play. They wanted their own systems in place. So each team wanted low latency in their own systems, right? So each microservice has their own data, which is added on to the main Docstore database. And so that is where the requests are being served, the write requests, the read requests. And each team wants everything to be done based on their needs. So their requirement should be satisfied. But the problem was that scaling this wasn't so easy, which we will see and talk about in 1 second. Before that, we know all about Docstore now. Let's talk about how it was designed in a very simple way. So the setup is very simple. It is made up of three layers. Now, the implementation is actually quite complex, but for the sake of this discussion, we are going to keep it very, very simple. So it starts from our microservice, which is where the application code is. It makes a request to the database. Now, the first layer that this request encounters is our query engine. Now, as you can see, this is completely stateless layer. So this layer is responsible for our query planning. Whatever query you give, it formats it in the way the database can read it. And then all the validations, all the health checks for your nodes, basically to ensure that these nodes inside the storage engine layer are alive or not. And a lot more things that can be handled over here, which I will not go to because it's not that important to the issue at hand. The next layer is our storage engine. Now, a thing about the storage engine is that there are a lot of layers. You can see that over here. And here we have something called a raft group. Now, if you don't know what a raft group is, I'll probably make a separate video dedicated on this concept on my channel, just to give you a brief so that you know what this is made up of. A raft group usually consists of multiple nodes, and that a raft algorithm basically is responsible for deciding which of the nodes will be the leader in this particular setup. So this is used for replication, and each partition, as we can see over here, that's partition 1, 2, all the way till n. These are all MySQL nodes, right? So partitioning is another concept we studied in the video on databases. That's what's happening over here. And this raft group is basically having a leader and two followers. So that's the setup that Uber has gone for, right? So a leader basically takes in all the requests to itself, and the data is replicated to the followers. So that's how things are scaled when it comes to Raft. Now then we have this CDC layer, which is the change data capture layer, this which is basically a part of the streamer. And this is something we will talk about in a bit. But these are the main layers that this Docstore is made up of. Now, what is the problem that Uber was facing over here? Because they were able to serve 10 million requests. So it's natural that they knew something about building good database designs. So what happened? What went wrong? Or what could have been improved? What did they try basically? So their limit had been reached when it came to database performance. So there's only so much you can get out of a machine. Now you would think that, Arindam, in your video, which is the very first video in the System Design Fundamentals playlist, which is on scalability, where I talk about vertical scaling, horizontal scaling. So go check it out if you haven't already. In that very video, I talk about how vertical scaling and horizontal scaling are two very viable options. when you are facing some issues like managing traffic, like Uber is having right now. So question is, why didn't they do that? Well, the answer is they did. But vertical scaling also stopped helping because the problem was in the database engine layer. It could only do so much. So it wasn't a problem, it was just a very natural limitation of that architecture. And then they tried, okay, fine, let's go for horizontal scaling. Let's add more servers. But it became too complex far too quickly. Not to mention, it was turning out to be 6 times costlier. So they didn't think that it was a very sustainable option in the long run. So even horizontal scaling, which is considered to be relatively cheaper, turned out to not be a good fit for them, which is why you need to think before implementing any solution, weigh out the pros and the cons, do some tests, because you can see that a solution that may work in theory may not work in practice. Now, another thing to note here is that Uber was facing a high read to write ratio. So for every row that was written in the database, it was read or fetched by users a lot more times. Right? So basically, every time a user wanted to read this data, they had to go to the database again and again and again. So that was increasing the load on their databases. So you would think that there is a very, very obvious solution, and that is, well, caching, which we covered in, I think, lecture 4 of the fundamentals playlist. So if you don't know what caching means, you should go check it out. Otherwise, you will not be understanding the rest of this video. I can promise you that. So the obvious caching solution, why didn't they go for that? Well, the answer is that they did that again. It's not that a system like Uber can exist without caching. It is very unthinkable of them to do that, right? So the way caching was implemented at Uber was that each team that I was talking about over here, each team, each business vertical and their microservices, they had their own cache. Each team was managing their own clusters. So the problem was that they were managing it on their own. So scaling wasn't turning out to be as effective for them. Each of them was handling their own invalidation, their own keys. So Uber thought that, all right, this decentralized way of managing cache and invalidating cache needs to be stopped. We need to come up with a system and an architecture that works for the organization as a whole. They were looking for an umbrella solution, because let's say there is one team who has built a good caching solution, another team may not have built it that way, right? So they wanted to build the best solution that could be used by all the engineers. So basically, some issues that these engineers faced were that if your system was deployed in multiple regions for fault tolerance, again covered in another video in the fundamentals playlist, there was something called region failures. So if, let's say, your servers are deployed in India and in Singapore, if the servers in Singapore crashed due to any reason, each team had to manage this particular part separately. So this was turning out to be quite an overhead, quite an engineering overhead, so to speak, that each development team had to manage it on their own, when in reality, one team could have just managed it and relayed the solution to the other teams, right? So they had a choice. Either you manage failovers on their own, or if something fails, you need to face latency because your caching solution will not work. Then you have to fetch data from the database every single time. So we go over to the next part, which is the solution. So what Uber did was they built an integrated caching solution. They decided to build an integrated caching solution. By integrated, I mean inside Dockstore, which is their in-house database platform. Inside Dockstore, they decided to add another layer, which is called cache front. Now this is a caching layer through and through. So the idea was that each team would not have to manage their own caching layer now. They could just use the Dockstore client library, which is their internal library, so not available for public use as far as I know. So they could use this library and use the caching features that come with it inbuilt. So that's what they wanted to build. The reason behind that would be that it's less disruptive because developers won't have to add a new caching solution that they may come up with. They could simply use the existing library and get done with it. This would also increase their productivity. So not only were they trying to solve for scaling problems, they were also trying to solve for productivity problems. So that is what they're going for over here. So question is then, if individual teams will not manage this, then who will? Well, the team that designed and built Bookstore was supposed to manage this. And that's what they did. Now question is, where does this caching layer actually go? This caching layer is integrated with the query engine layer. So if I just go back over here, you would see that this is the query engine layer, which talks to the storage engine once the query is processed. So right over here, they've added a layer of Redis. So this is where the caching solution exists. Now this is a black box which we'll be diving deeper into. So the question is, if we are adding another layer over there, does this come before the storage layer? Do all queries have to go through this caching layer first and then to the database? Well, that's the best practice, but as any good system would allow you to do, this was made to be completely optional. So all developers who wanted this functionality could use it, especially ones that were facing scaling issues. They had to use it. Otherwise, it was completely optional for them. Now, I'll get into this part in a second. It was optional and it was also highly configurable, which meant that teams could implement caching at the database level as a whole, or they could do it at a table level, or they could even do it at a request level or certain endpoint level. So this is some flexibility that they had in mind while trying to design the system. What I mean by optional over here is that Uber has a lot of use cases where they want strong consistency. So when you want strong consistency, caching may not be the best solution for you. For example, in Uber Eats, which is Uber's version of Zomato or Swiggy, if you're not familiar with it. So in Uber Eats, there is a shopping cart and there is a restaurant menu. So try to pause this video and think which of these cases would need a stronger consistency as compared to something like eventual consistency. Alright, so the answer is the cart needs stronger consistency, because whenever a user puts something in the cart, their likelihood of ordering within the next few minutes is very, very high. So they want strong consistency in their cart. They can't afford any discrepancies in user experience over there. But when it comes to the menu, they can still cache that menu because it doesn't change as often. So that is why they had to make this feature as optional for the teams. So that's the solution that they thought of. Now, this solution uses something called a cache aside policy. So what happens is very simple. The request comes to the query engine, that is the first level in our doc store. That query engine tries to read data from cache, the Redis layer, and it tries to get it. Then it may have the complete solution, it may not have the complete solution. In case it doesn't have the complete solution, it fetches the rest of the rows from the database. And once it does, it then updates the rows back into the cache so that the next time the user requests for this, it is already available and the database is not visited in that particular case. So that's that for our architecture, our theoretical architecture of this solution. Then what else did they do? They also had an idea about cache invalidation, because that's something that's usually extremely tricky, and that's something I say from personal experience. So they decided to put something extremely simple to tackle that. They said that, you know what, no matter what your request is, the default time to live for the data in cache would be 5 minutes, and that's it. If you want to override that, you have the option. Like I said, it's configurable. So if you do not want any time to live over there, you can avoid it. Otherwise, your data will go stale in 5 minutes, so it should be removed. All right. So it will not go stale, but it will definitely be invalidated after 5 minutes. So there is that. Now question is how do we effectively keep our data in our cache? Because the idea is that the database should be visited as fewer number of times as possible, right? So to achieve that, the requests have to go to the cache on priority. So how did they achieve that? They did that via CDC, which is change data capture. And this is done via something called Flux. All right. So the idea was that when something gets updated, cache also should get invalidated, right? So usually what you can do is you can make a separate query to the cache, separate query to the database, but this time since the client is the same, they wanted something built in that if I update my database, my cache should also be updated. And in case my data is turning out to be stale in the cache, it should be invalidated. So the way they did this was via a background process, like I said, via Flux. So this comes over here in this third layer, the CDC, which is change data capture. What I mean by change data capture is that every time there is a query in this database, it is logged somewhere in the system. Every single query is logged one after the other. There is a component that reads all these queries. Let's go back to that page. There is a component that reads all these queries and updates it asynchronously to Redis in the background. So what happens over here is we write something to our query engine that will update data in my database. Nothing has been updated into the cache yet. Now there are my MySQL logs which go over and are processed via this change data capture system, which is managed by Flux inside Docstore again. This Flux then updates Redis via the backend. So this is what's actually happening over here. So the next request, then it comes in, it reads data from Redis, and if there's data missing, it reads it from the database and then writes it back to Redis. This is the flow that they're going for over here. All right. So like I said, it's again highly configurable, and if they want to just not have Redis as a part of the process, there was a dedicated API to allow that behavior so that they can achieve even stronger consistency. Then one thing I would like to talk about over here is the way they store data in Redis. So usually when we store data in Redis, it's a simple key value pair, right? So you have a key which is something unique to your system, and then there is its value, which is the data, a very simple JSON, stringified JSON that's stored, mapped to your key. But one reason why I wanted to put it in this video, put this particular diagram, was that Uber, what they did was they really defined their key in such a good and organized manner that I felt like it's worth mentioning over here. So their key, it starts from the table, then there's a partition key depending on the database partition, then a row key, which is basically a different sort of key that is different from the partition key, and then the instance. So basically Docstore can have multiple instances, and which can call the same cache instance. We need to have some sort of distinction between the keys on the different instances so that you don't end up overriding some data, right? Because the same data can be stored on different Docstore instances in a different manner. So we have to find an identifier to help us differentiate between those as well. Then we have the value. So even the value is very nuanced. It has the version, timestamp, expiration, then flags, the shard ID, encoding, and then comes the actual data. All right, so this is how they store it in the Redis, and they've given some examples. So you can just pause this out and read it and see how it compares to what we see up there. All right, let me just zoom this out for you. You can pause it and read it. So the reason why I put this in is because, like I said, it's very organized, and this is a good practice to have in scalable systems. So not just to scale your database, but to keep things neat and findable should you need to. Because if you want to maybe see a Redis key that is getting way too many calls, you'll be able to tell at least which database instance it is mapped to, given this particular format. We still had one unsolved problem, that is region cache failover. Now I mentioned this earlier as well, that here each team had to manage region failovers on their own. This problem still wasn't solved using this architecture. So question is, how do they do that? And the answer is that you can use Redis write stream for replication. So let's say you have one server in, let me just show that to you. Yeah. Let's say you have one server in India, you have one server in Singapore, same example as before. One of them goes down. The problem here is that all the requests that were coming to your Singapore cluster, they will be redirected to the database because we will be having a cache miss, and it will be pretty bad because the problem that we are trying to solve, that is less number of hits on our database, will not be solved in such a case. So what we want to do over there is try to have this Indian server also have my cache data so that the requests can then be redirected over there. So the question is, how do we do that without adding more overhead to developers who might have to push it to the cluster in Singapore and the cluster in India? The solution, Redis write stream, was very similar to this change data capture that we talked about earlier. So the way it managed things was that even Redis has certain logs, right? Everything that is written to Redis, it was also logged, and then they had a component that was reading those logs, and it was then reading it from, let's say, the Indian servers, sending it all the way to the Singaporean servers, and that is how it worked. So it was a pretty interesting way that they went about it. So let me just take some space up here. So let's say we have our Indian server. This is the Redis server, by the way, and a Singaporean server. Sorry, Redis server belonging to the Singapore region. So let's say if I receive a request on the Indian servers, how do I send this data to the Singaporean server? So like I said, there is a write stream. So everything that is written to Redis goes to this write stream after the data has been put on to this server. This data would then, what it would do is, in the background, all of this is happening in the background, by the way. The user is not impacted over here at all. It calls the database in Singapore, gets the data from the Singaporean database, then updates it to the Redis cluster in Singapore. So that is how it ensures that data is not only replicated between India and Singapore, also that the data that is sent to the Singapore server is consistent with the Singaporean database. Alright, so that is a very good thing that they did, which I felt like it is also worth mentioning. So that's how they replicated this data, and this also solves another problem actually before I move on. That's what's called cache warming. So in case of a failure, they wanted to keep the cache warm. In case there were more requests coming into a certain region than expected, the cache already has the data associated with it. That is what it's called, cache warming. All right. So now question is, how do we ensure that when a node goes down, when a Redis node goes down, there's no latency associated with it? Because if something goes down, whether it's a database, if you're not able to connect to it, or if you're not able to connect to a Redis node, what happens is that it continuously tries to make requests, and there is a timeout associated with it, which could be a few seconds. It could be, let's say, 5 seconds, it could be 30 seconds, could be anything. So we can't make the user wait for 5 or 30 seconds. Our system will inevitably crash if we wait for that long, especially if we do it synchronously. So the solution was to have a sliding window circuit breaker. And this is the first time I was hearing about this concept. So the idea was that they would have a sliding window. So let's say this is window 1, which went from minute 0 to minute 1. This is window 2, which went from minute 1 to minute 2. Then we have our sliding window, which keeps on moving with time. At first it is here, then it will go there, something like that. So the idea is, it will take in all the errors, that we encounter over here and all the errors encountered in this entire window. It will sum them up and it will check is the number of errors encountered over here in this window, is it acceptable to us? That number is defined by them. Let's say 10 errors in 1 minute, which could be, it is an arbitrary number that I'm giving you. It could be different in their practice. So if the number exceeds what they expect, they would simply shift their traffic to the different to a different Redis server. So that is how they've implemented circuit breakers so as to not have too many errors and too many unexpected failures. So they have a backup plan, and this is how they chose to implement it. So very unique strategy, which I've never really seen in practice in any other place. Then there are many more implementations that they actually ended up doing while they were designing this cache front system. So one of them was cache deduplication, because sometimes when you update the cache, especially via the CDC, what ends up happening is that you may end up receiving stale data in your cache. Sometimes you may use cache aside policy, sometimes you may update it via the CDC. We want the latest one. That may not always happen. So in their blog, they talk about cache deduplication. I won't go too much into the details. They also talk about negative caching, which basically means that when there were some queries made to the database where the result was expected to not be anything, it was expected to be empty data, they cached that as well, and they tried to do it preemptively. Then some adaptive timeouts in place, and lastly, they had some sharding implemented for the Redis clusters as well. That is peak optimization when it comes to caching. So this is something that I highly recommend you go and check out in their blog. Otherwise, this video will be 40, 50, 60 minutes long. I'm sure you guys don't have the attention span for it. So I'll be pausing here when it comes to discussing the theory and the deep dive, and moving on to what they actually ended up achieving. So the results was that P99.9 latency came down by 67%. So that means 99.9% of the requests, whatever time they took earlier, that was down by 67% now. Then we have 99% cache hits at 6 million requests per second, which is a great number and basically indicates that the problem that they were trying to solve had been essentially solved. And successful failover handling was also reported by them, because of course they must have tested the whole system out, and they diverted traffic from one region to another, and their background replication actually ended up working. So that's another success in their books. Lastly, when it comes to cost, like I mentioned earlier, vertical and horizontal scaling was turning out to be quite the costly affair. Vertical scaling was not helping at all, and horizontal scaling was turning out to be very, very costly. So they did a comparison on how much uh, processing power they would need for this particular data, 6 million requests per second. They came to the conclusion that if they just had to use the storage layer, which is in the initial diagram, the storage engine, if that is all they had to use, they would have needed 60,000 CPU cores. They would have needed 60,000 CPU cores as compared to the 3,000, just 3,000 Redis cores that they ended up using for this particular implementation. So those are the achievements of this particular implementation, which was, as of 2024, serving 40 million requests per second. So that's that for Uber. In the next video, we'll cover another very cool case study. So stay tuned and follow for more.